Hello APC Mechanics students in Unit 7 in Gravitation, Class 4 7.1 in Gravitational Forces, Part 4. Exercise 1. Two satellites of masses m1 and m2 orbit a planet of mass m in circular orbits. The moment they mention circular orbits, it means that we can use the relations given by v is the square root over gm central mass over r, and the period is given by square root of 4 pi square r cube divided by g central mass. Remember that this is an MCQ. We're allowed to use these directly because the solution, the steps are not important, unlike a free response. The satellites travel in opposite directions with the speed v1 and v2 as shown in the figure above. Their orbital radii is given by r1 and r2 respectively. Assume that m is much greater than m2 and m1. The ratio of the speeds v1 over v2. So let me do it. v1 over v2. That would be the square root of g central mass r1 over the radical of g central mass r2. Central masses and g, they cancel. That would be 1 over radical r1, 1 over radical r2, which is basically radical 2, radical r2 over radical r1, making the correct answer to be A. Exercise 2. An astronaut on a new planet is hanging various objects with different known masses, one at a time, from a spring scale. The astronaut records the mass of the object and the force readings from the spring scale in a data table and constructs a graph. The astronaut is interested in determining the gravitational field strength G on the surface of this new planet. Which of the following indicates how the astronaut should construct a graph to determine G of the new planet and identifies the characteristic of the graph that is equal to G? Now we know that we should graph the force. We can directly eliminate, or possibly we can also graph the mass. So if we graph the force as function of mass, the slope would be g. This is correct because we know that F is equal to mg. Now if we're doing Fg versus g versus m, indeed the slope would be equal to g. Exercise 3. Satellite X moves around Earth in a circular orbit of radius r. Satellite Y is also in a circular orbit around Earth, and it completes one orbit for every 8 orbits completed by X, which means that the orbit of satellite Y is greater than that of X, and in particular it is by a factor of 8. Then the period of Y is equal to the 8th period of X. What is the orbital radius of satellite Y? Now, because we're talking about perfectly circular orbits, then the period is given by the square root of 4 pi r cubed gm. And now we can say if the period of y is equal to the 8th period of x, then that would be the square root of 4 pi ry cubed divided by gm, which is equal to 8 the square root of 4 pi rx cubed divided by gm. Now gm with gm cancels, 4 pi with 4 pi cancels. Now that would be the square root of ry cubed equals to 8 the square root of rx cubed. Now we can square both sides, so that would be ry cubed is equal to 64 rx cubed. But notice that the radius of x is given by r and not rx, so this is equal to r, which means ry cube is equal to 64 r cube. Now taking the cubic root on both sides, that would be ry. The cubic root of 64, that would be 4 r, and the correct answer in this case is D. Exercise 4. A particle of mass m is released from rest and the initial kinetic energy is 0, a very large distance from a planet of radius r and mass m. At this distance, the gravitational potential energy of the planet particle system is nearly 0. So the initial kinetic energy is 0 and the initial gravitational potential energy is 0. But the particle experiences a very weak gravitational attraction toward the planet and no other forces. The graph shows how a quantity on the vertical axis changes with the distance r between the particle and the center of the planet, but the thing is that they didn't tell us what is this quantity. Which of the following could be the quantity on the vertical axis? Now the gravitational force, this is not correct, because we know that the gravitational force as function of r, it's proportional to 1 over r square, and we know that the shape of the curve would be hyperbolic. So that's wrong. Now, as well as for the potential energy, as well for the acceleration, because the acceleration is also proportional to 1 over r square, and the potential energy is proportional to 1 over r. We can directly eliminate these. Now, what about the kinetic energy? We can also eliminate the kinetic energy, because as function of r, because the potential energy changes, then the kinetic energy will change, because the energy overall is given by kinetic plus potential. And here, if we're considering the system is isolated, then this is constant. As u varies, then k will varies as well. So we can directly eliminate the kinetic energy is not constant. The only constant quantity is the mechanical energy, and that's correct. So this is the correct answer, especially that our initial conditions is given by 0 kinetic energy and almost 0 gravitational potential energy. For this reason, the mechanical energy will be represented by a horizontal line. Now, a satellite of mass m in a circular orbit of radius r about a planet of central mass m, the period of the satellite is t. A second satellite of mass 2m in a circular orbit of radius 2r around the same planet, the period of orbit of the second planet. Since we're talking about circular orbits, then we can use the fact that the period is given by the square root of 4 pi r cubed divided by gm. But here you need to pay attention that m is the central mass and not the mass of the satellite. Now r changes by a factor of 2, the central mass remains the same, so that would be given by the square root of 1. R cube would be 2 to the power 3 divided by 1 multiplied by 1. I repeat again, m is the central mass and not the mass of the satellite. Even if the mass of the satellite changes by a factor of 2, that would be radical 8, making D to be the correct answer. Two identical satellites orbit a planet of radius r in circular orbits A and C of radii 3r and 12r respectively, as shown above. How does the magnitude of the gravitational force Fa between the planet and the satellite in orbit A compare to the magnitude of the gravitational force Fc between the planet and satellite in orbit C? Since we're interested in determining Fa in terms of Fc, so we will calculate the ratio Fa over Fc, which is basically Gmm divided by Ra square over Gmm divided by Rc square. Now we're assuming that the satellites are identical and the central mass is the same. That would be Rc square divided by Ra square. Now Rc is 12r to the power of 2. That would be 3r to the power of 2. So basically it would be 4 to the power of 2, which is 64, which is 16. Then Fa over Fc is 16, which means Fa is equal to 16 Fc, and E would be the correct answer. Two identical satellites, again the same given. The speed of satellite in orbit A is VA, and for C it's VC. We need to determine the ratio of VA over VC. We can directly eliminate potential answers that are wrong. Now A is closer to the planet, which means VA is greater than VC, which means VA over VC should be greater than 1. We can directly eliminate A. B, they are not equal, so we're left with C, D, and E. VA over VC, that would be the square root of GMRA divided by the square root of GMRC, which is radical RC over radical RA. And that would be the radical of 12r divided by the radical of 3r, which is basically radical 4, and that would be 2. Then VA is the double of VC, making C to be the correct answer. Two moons of equal mass are in circular orbits around the planet. Moon 1 orbits with a radius r and Moon 2 orbits with a radius 3r. What is the ratio of the magnitude of the planet's gravitational force on Moon 2 to that on Moon 1? So we know that the planet will exert a pull of gravity on Moon 1 and a pull of gravity simultaneously on Moon 2, there will be a gravitational force between Moon 1 and Moon 2, but we're not taking that on consideration. So F2 over F1, that would be G m over R2 square, and the G m over R1 square. Because the moons are of equal mass, we can use the cancellation effect. That would be R1 square over R2 square. Now R1 is R and R2 is the triple of R. Then basically that would be 1 over 9. And the correct answer in this case would be E. A small satellite of mass m starts at rest on Earth's surface and is then launched into orbit at an altitude r equal to the radius of Earth. If Fs is the gravitational force of the satellite at the Earth's surface, and that's Fo, we need to determine the ratio Fs over Fo. We can directly eliminate potential answers knowing that Fs is greater than Fo and they are not equal, so it's either A or B. Now that would be Gmm over Fs, which is basically R square, over Gmm over the double of R square. So that would be 1 over R square and 1 over 4R square, which is basically 4R square over R square, which is 4. So Fs is 4 Fo, making A to be the correct answer. Two moons are in circular orbits around the same planet. Moon 1 has an orbital radius r and orbital period t. Moon 2 has an orbital radius of 9r. What is the orbital period of Moon 2? So circular orbits, it means we can use the previous relations that we talked about, and we need to apply the factor of change. Then the period is given by the square root of 4 pi r cube divided by Gm. We only change the radius by a factor of 9. That would be 9 to the power 3, which is basically 27, making E to be the correct answer. Now a rock weighs 2 Newton on the surface of Earth. This is important. We can directly know that the mass is given by 0.2 kilograms because on the surface of Earth G is 10. How far away from the center of star? So we need to find the radius. We know the mass of the star, which is the central mass. Must the rock be in order to exert the gravitational force? We know that Fg is given by 2 newtons. Now, according to universal law of gravitation, F is given by G m over r square. Then r in this case is given by the square root of G m divided by Fg, which is basically the square root of 6.67 times 10 to the power minus 11. One of the masses, which is the mass of the rock, is given by 0.2. The other mass is given by 2 times 10 to the power 30. And the pull of gravity is 2. Now plugging this on the calculator, that would be given by 3.65 times 10 to the power 9 meters, making A to be the correct answer. And finally, exercise 12 as an exit ticket for today's video. A satellite is orbiting Earth at an altitude of 1/2 Earth's radius. The moment they mention altitude in the exercise, be careful. We can't apply directly the factor of change. Let's draw a figure in order to understand what's happening. This is the Earth. That's the radius. That's the altitude. The altitude is given by half the radius. If the weight of the satellite while in orbit is 9,000 newtons, what is the weight of the satellites on Earth's surface? So the initial radius is given by R1, is given by R plus half R, which is 3 over 2R. I didn't mean the radius, but I meant the separation distance, which is the distance from the center to the satellite itself. Now R2 is the new separation distance in which the satellite is located on the Earth's surface and is given by R. In order to know, or in order to apply the factor of change, we need to know the factor between the new radius and the previous radius, which is basically R2 over R1, and that would be R over 3 over 2R, and that would be 2 over 3. Then we can say that the radius changes by a factor of 2 over 3. And now we can apply the factor of the change for the weight. The weight represents the pull of gravity. That is given by G m over R square. everything is invariant except for the radius, that would be 1 over 2 over 3 to the power of 2, which is basically 9 over 4. But notice that they don't want the factor, they want the value, so simply we will multiply by 9000. Plugging this expression on the calculator, we're gonna find a value of 20,250 newtons, making E to be the correct answer. And that's it for me in this video, guys. See you soon in a new one.